Hello, and welcome to another topic in chemistry. You can go ahead and start setting up your notes. Our focus for today is the quantum mechanical model. If you are watching this on the day it was originally assigned, you can fill in the date. We're in Unit 7, Day 3. If you're watching this video for any other reason, welcome. I'm excited to teach whoever is listening to this video about the quantum mechanical model. The essential question that we will be answering in this video is, how does the quantum mechanical model describe the electron cloud of an atom? So you're starting this video and it is assumed you already have kind of an idea of what an atom looks like, but this video gives you lots of really small details that will help you understand more about how light is produced, and then eventually this will lead into some more details to help you understand bonding as well by understanding the details of the electron cloud. All right, let's get into it. So the first thing I want to do is just a super fast, just kind of review of atomic models throughout history. So when we started, this is kind of what Dalton would have said, just kind of a sphere, right? But then eventually other scientists started doing more research, more experiments. And so then we came up with this, we being scientists, came up with this idea that there's like positives and negatives, so electrons, and then just a whole bunch of like a positive mush, basically. And then eventually we realized, no, the positive mush is not just everywhere. That positive is in the middle, and we call it a nucleus eventually. And then those electrons are on the outside. The positives and the negatives balance each other out. And then eventually we're like, but it seems like those electrons aren't just randomly placed, they're more in specific energy levels. And then eventually the neutron was discovered. So that's kind of the history of the different atomic models, changing just little things at a time as new pieces of information were discovered. So that's kind of where we left off in terms of the structure of the atom. What we're going to talk about today is one step beyond this structure, getting way more specific of what that electron cloud looks like. And that is known as the quantum mechanical model. And it was discovered or kind of established by a guy named Ernest Schrödinger. And what he did was he said, let's use a little bit more of our technology and some math functions and kind of graph what that motion of the electrons looks like. So the motion of the electrons, he came up with this Schrödinger equation. So it's this fancy math equation that helps us map out the electrons. And we can think of the electron then as a wave pattern, because waves have measurements and patterns and numbers, and the mathematical equation has patterns and numbers. And so then we can get a more detailed picture of what that electron cloud looks like. It doesn't define the exact path of the electron. It's more like at a moment in time, where would an electron be? Where is it expected to be based on the Schrödinger equation and the mathematical probability of that wave pattern? Continuing on here, so again, it's more the probability of where the electrons would be, but from what we can tell, it's a very good probability, about 90%. So when we use the Schrödinger model or the quantum mechanical model, and we say, oh, the electrons are located here and here and here, it's about 90% that at any moment, that is where the electron would be. In analogy, it's about the same as like the probability of you doing your schoolwork on time. Probably a 90% chance. Most of you know you got to get your schoolwork done, but maybe you had something come up, you got distracted, you needed help, so you didn't finish it on time. But I would say, 90%. So it's a pretty good probability, the Schrödinger equation and the quantum mechanical model. So that's kind of the historical background of it. Eventually, with the Schrödinger equation and the quantum model, you put it all together, we start to get something this like bluish, this light blue color. It's basically this blurry cloud of a negative charge. So if we map out an electron cloud, it starts to look more like this than like the example of the other pictures of models that I just showed you. Okay, so again, that's kind of the historical background of where we're coming from to get to today's model. Go ahead and do a level 1 question so far. Remember, there's a Costa question guide on Schoology if you need some examples of some good sentence starters for questions. Otherwise, pause the video, kind of look through what you did, get your notes caught up, make sure it just kind of makes sense. Level 1 question, come back when you're ready to go on. All right, so one of the things that I said is the biggest advantage of the quantum mechanical model is that we get really specific about the electron cloud. So what we need to do is we need to break apart that electron cloud into more and more specific pieces, eventually getting to something called an atomic orbital. So an atomic orbital is the part of the electron cloud, region of space, where you're going to actually find the electron. So it's kind of like, imagine, if you were to say, oh, you live in Minnesota. Okay, well, that's not very specific. That's just like saying, oh, the electron is in the electron cloud. So then, like, if you want to find you, like if someone's going to mail you something, you can't just say Minnesota. You probably also need to know what city, what street you live on, maybe your apartment number or your house number. So just getting more and more specific. That's what the quantum mechanical model does. It just gets more and more specific about where to find that electron. So we have these things called quantum numbers, and we're going to talk about two of the quantum numbers. There's technically four, but the principal quantum numbers are going to help us understand more about where to find that electron. The symbol for the principal quantum number is n, and n is either 1, 2, 3, 4, 5, 6, or 7, and it corresponds to the 7 different energy levels around the nucleus. So if you have an n of 7, that is the highest energy level that we have either created or discovered of the elements that are currently known or made. Energy level 1 would be closest to the nucleus. That would be our lowest amount of energy for electrons. Energy levels are like rungs of a ladder you can't stop between. So there's not like a 1.8 level or a 3.2 or 6.5. You're either staying on 1 or you go all the way to 2. Stay on 2 or go all the way to 4 if you got lots of energy added, that kind of idea. So you can't stop in between them. But that n is energy level, and that is your principal quantum number. Now, the other thing that the energy levels will do, so you have that principal quantum number, and then you can divide it into sublevels. Okay, well, that kind of makes sense. An energy level is like a big area. Let's get more specific and let's divide it into sublevels. So the sublevels the number of sublevels match what energy level is in up to 4, because there's only 4 sublevels total. So what I mean is energy level 1 only has 1 sublevel because it's small, right? So it makes sense you can't divide it very much. Energy level 2 has 2 sublevels. Energy level 3 has 3, 4, 5, 6, and 7 all have 4 because the maximum of sublevels is 4. So energy level 7 still only has 4 sublevels because we don't have any other ways to divide it. All right. Another way you can think of this is like, let's say you went to a concert, when that's safe again, dream about when that would happen. So the idea is that you get your ticket and it tells you, if it's not general seating, if you have an assigned seat, it might tell you which floor are you on, which section, and then eventually what row and what seat. Well, again, that's kind of what we're doing with the electron cloud. So instead of just saying, the electron is in the electron cloud, what energy level is it in? What sublevel is it in? Eventually getting to a really specific, like the seat in that concert hall would be your atomic level, okay, or atomic orbital. All right, so there's 4 sublevels. So again, there's 7 energy levels. Each energy level is split into at least 1 sublevel, maximum 4 sublevels. And the sublevels are different shapes. The S is the simplest sublevel, and it's just a sphere. So the electrons are moving around 3-dimensional, X, Y, and Z, different orientation in space. You have 3-dimension sphere. The P is a little bit more creative because now you've got more electrons, because now you have a second sublevel. So the electrons are kind of going in a different pattern to try to stay away from each other. And that dumbbell shape can be oriented on X, Y, or Z. And remember, Z would be like coming out at you, like, and behind you. Like that's what we mean by kind of the 3rd dimension. The D is kind of a complex shape. It can be kind of like a flower pattern. F is also. So energy levels are 1, 2, 3, 4, 5, 6, and 7. Sublevels are S, P, D, and F. So again, what I'm giving you is the details of the electron cloud so that you know more about the big picture of light, energy, and bonding. That is why we care about the details as chemists. So the complex shapes just are different creative. This kind of looks like a flower. This is kind of like an X shape sort of. The only ones I would ever expect you to like draw or know by sight would be the S and the P, because the D and the F can be really complicated depending on how many electrons there are. Okay, so energy levels are split into sublevels. The sublevels show us the shape of the electron cloud, S, P, D, and F. Okay, going to a level 2 question, kind of process what we have so far, maybe compare and contrast energy and sublevel, compare and contrast an S sublevel and a P sublevel, how many, well, actually that might be a level 1 question. I was gonna say how many sublevels are in energy level 3? That might be a level 1 kind of question. Anyway, pause the video, process what we've talked about so far, and then write your level 2 question. Come back when you're ready. All right, so remember, the focus of this set of notes is understanding the electron cloud more, trying to get to the atomic orbital, but we haven't talked about that yet. We've talked about energy levels to sublevels. Our next thing we're going to talk about is the orbital. So again, energy levels are split into sublevels. Sublevels go down to orbitals. An orbital is the region of space where the electrons would actually be located. So again, like if you went to a big concert or a fancy play and you had a ticket that told you what your seat is, it might tell you the section and the row and the seat. Just like in an electron cloud, we have the energy level, the sublevel, and now the orbital. And the S sublevel, which is that spherical shape, has one orbital. Because remember, this is the simplest one, the smallest one. So it can just have one orbital. So there's just one place where the electrons can sit. The P is a little bit more complicated, so it's a little bit bigger. The P sublevel can have 3 orbitals in it. The D has 5 orbitals, and the F has 7. So you can see that pattern, 1, 3, 5, 7. So the orbitals fit into sublevels. The sublevels have different shapes, and the sublevels fit into energy levels. So again, getting more and more specific. If you just think of the electron cloud as just a bunch of electrons flying around, how would we ever find the electrons that are taking part in bonding or the ones that are moving up and down energy levels to produce light? We have to know the details to really understand what's going on. So the orbitals are where the electrons sit. Orbitals fit into sublevels, sublevels fit into energy levels, and the energy levels make up the electron cloud around the nucleus. I've got one more little division for you. It turns out that two electrons can fit into one orbital. So if I'm trying to actually find the electrons, there could be 2 in any orbital that I had. So for example, the S sublevel, which is spheres, is 1 orbital, but that's really 2 electrons. The P, which is that dumbbell shape, sublevel, has 3 orbitals, meaning that the P sublevel could hold 6 electrons total. D can hold 10 electrons total. F can hold 14 electrons total. And it turns out that what happens is when this sublevel this orbital is filled, then we go to the next set of orbitals and the next set of orbitals and the next set of orbitals. So when you're like filling the electron cloud, which is what we're going to talk about in the part 2 of these video notes, is you have to think about, oh, when is the S sublevel filled? When do I go on to the P? When do I go on to D? But remember, in energy level 1, there's an S. In energy level 2, there's an S and a P. In energy level 3, there's an S, a P, and a D. And in energy level 4, there's an S, a P, a D, and an F. And then remember, energy levels 5, 6, and 7 also have an S, P, D, and F. So that's how we eventually start building up the electron cloud. And that, again, I'm getting a little bit ahead of myself, but just to kind of help you try to make some connections of where we're going with this and what does this all mean, that's the idea. Okay, a couple little extra things. The sublevels determine the shape of the electron path, and the energy level determines the size of the electron's path. So for example, if I had an energy level 1 sublevel S versus an energy level 2 and a sublevel S, notice that the S is the same. So the sublevels are the same shape, but the energy level 1 is half the size as energy level 2. So this would be, can you imagine, picture this in your mind before I show it to you. What would look different about these? Or draw it really quick. Do you get it? Yeah. So a 1s is a small sphere and a 2s is twice as big, or maybe not exactly twice as big because that doesn't always happen. But the point is that 2 is bigger than 1. So the 2s is bigger than the 1s. Okay. Well, what about a 3s versus a 3p? They're both 3s, which means they should be the same size, but an S and a P, remember what those shapes look like? Because sublevels are shapes. See if you can draw it or picture it quick before I show you. Take a moment, think. What does S look like versus P? All right, so an S is a sphere and a P is a dumbbell. But if you were to measure it from here to here, it's the same distance as from here to here. So even though the shape looks very different, the size is the same in a 3S and a 3p. So sublevels determine shape, energy levels determine size. And then eventually it would start to look like this. Look at this beautiful picture. If you need a tattoo idea, here you go, a beautiful electron cloud. So the idea is that you've got your nucleus in the middle, and then look at, you've got a 1s, that's this little circle. You've got 2p orbitals, that's these dumbbells, and then you have a 2s, or sorry, this one is the 2s, and then you've got your 3s. So you've got a 1s, a 2s, a 2p, and a 3s, because that's how many electrons were in whatever element this was. But this is what the Schrodinger model, or the quantum mechanical model, is showing us, that it isn't just random electrons in those kind of rings like you think of, like the Jimmy Neutron picture. It's actually interesting different shapes that are showing us where those electrons are located, and they just kind of build out three-dimensionally. All right, go ahead and do a level 3 kind of question. Maybe something like, sort of the question of like, why do we use this, right? Defend why we need to know about the details of the atomic orbitals, so you can make that connection. And then your summary should answer our EQ for today. That is the end of part 1 of these video notes. So finish up your class of questions, do your summary, and then there is a second part of these video notes. You could either do those right now, or you could do it tomorrow, because tomorrow is asynchronous and there won't be anything new assigned other than finishing these notes. And then again, if you're watching this video during trimester 3 in 2021, then you've got other things like finish up the flame test lab. The review sheets from last week should be done. So just some other things to work on that you could work on now if you're not going to do the video notes, or do the video notes, do these things later, but just making sure you're getting some of those things wrapped up. And then just a reminder, I have office hours on Monday and Thursday from 2:15 to 3:15, and on Fridays from 1:30 to 3 if you need any help. Otherwise, that's it. That's the end of part 1. Thank you for your attention and your focus as we understand more about chemistry, specifically the electron cloud. See you next time.